Hi everybody. So up to this point we've been talking about refraction, the bending of light as it goes through from air, for example, to another material like glass, Pyrex, things like that. One of the things that we haven't discussed though is that the index of refraction actually depends very slightly on the color of the light coming through, specifically the wavelength. Remember, the wavelength determines the color. And so this has some pretty large effects. And when you look in your book, you're going to see that blue light in diamond has a slightly higher index of refraction than red light. Well, as you know from what we've worked with before, what that means is that the blue light is going to get refracted differently than the red light. It's going to be refracted at a different angle. This is actually why diamonds sparkle, because remember, the idea is to get total internal reflection. We want that light wave to be bouncing around. So they cut the facets so that we get total internal reflection. But because that angle is different for blue light than it is for, say, red light, then different colors will come out of different facets. This is what makes a diamond sparkle with all these different colors from there. Even though white light is coming into the diamond, remember white light has all the colors mixed together, but when it bounces around, when it finally escapes, the blue light and the red light will be coming out of different facets depending upon the angle to that light that you see. So let's take a look at this and let's see how we can actually use this to do some science. Let's get started. So diamond isn't the only substance for which the index of refraction of blue light is different from the index of refraction for red light. In fact, practically all substances have this. Now, in many things, it's not very different at all. And so when the white light hits it, you don't get a whole lot of that dispersion, but it's almost always there. So we can use this principle to make something we call a prism, and you've probably seen one of those before. And so we've got the diagram for it right here. Let's just go ahead and make that a little bit bigger. Now, prisms are generally going to be a triangle of some sort. The reason for that is if you think about it, and looking at microtask 1, we couldn't have just a flat piece, right? If it looked like this, then, well, obviously it's just going to go straight on through. Even if I come at some angle, there's not a lot of room for that dispersion to occur before it comes out. There will be some, and even with a telescope, if you use glass lenses for your telescope, there is a little bit of that dispersion. It's called chromatic aberration. But what we want to do with a prism is we want the dispersion, so we want it to be as wide as possible. And so having a design like this, where the white light comes in, and then we actually get dispersion that looks like this, which then will get refracted even more coming out. So take a look on the next page. And you can see kind of an example of how that works. So which form of light is going to be refracted the most? Now remember that we said blue light has a higher index of refraction. So the speed of light is slower for blue light than it is for red light inside this material. So which one is going to have the higher refraction? Well, that's going to be the blue, right? Because the higher the index of refraction, the more it's going to be bent. So which color will be seen at the top of a rainbow produced by the prism? So let me draw our prism here again. So the light comes in and the blue light is getting diffracted more than the red light, like this. So when we look at the rainbow then, which color will always be produced on the top of the rainbow? Well, as you can see, that's going to be the red. And the reason for that is that the red isn't getting refracted as much as the blue light is. So you've obviously, hopefully, seen a rainbow in the sky. If not, get a life. But what causes the rainbow is that there are water droplets up in the atmosphere. And so we've got this diagram here, which might be a little hard to see. So we'll make that a little bit bigger, but hopefully you can see it in your own workbook. So here's a water droplet. When that white light from the sun comes in, water also diffracts and refracts light of different colors differently, just like pretty much all substances. And so as you can see here, the red light doesn't get bent as much. Oops, we didn't switch to red. There we go. The red light doesn't get refracted as much as the blue light. It gets bent. But then it's going to reflect off the back of the water droplet. And so it gets reflected and then it gets refracted again. so that you get a fairly dramatic spread. Now, what makes the rainbow that you see in the sky then is there are all these billions of water droplets suspended in the air. So there'll be one here and one here and one here and one here and one here. You're down here at the bottom, on the ground, and in this case, the blue light, if I can get it to draw, the blue light doesn't reach your eye, but the red light does, and vice versa. So depending upon the positioning of all of these, you're going to see only one color from each drop that's suspended in the sky. And so what you see then, when you see the rainbow, you're actually looking at water droplets. But the only thing that you can see with that is that one specific color from that one water droplet. And that's what's going to make your rainbow. So this is why rainbows are generally the brightest either when the sun is low on the horizon, because we want it shining almost horizontally in there. So early in the morning or late in the evening are going to be the best time to see a rainbow. And obviously you have to have a lot of moisture in the air. Now here in Arizona, okay, that doesn't happen all that often, but we do get rainbows whenever we have one of our monsoons, when we get lots of the water droplets. And they have to be fairly big droplets. Small droplets, remember, they're not going to travel very far, and so you're not going to get as much dispersion. So really it's only after storms. There's water, even here in the desert, there's water in the atmosphere all the time, but those droplets are too small to see any really appreciable dispersion with that. However, when it's a storm, you're going to get these great big water droplets forming. That's when you're going to see it in the air. So where will you see the rainbow? And some of you may have noticed this before, but some of you may not have thought about it. So let's draw our horizon here. And so you're standing right here, and you want to see a rainbow. So if the sun, say, is over here, where am I going to see the rainbow? I would have to see the rainbow over here. The reason for that is because I need that water droplet, I need it reflected back. I will never see a rainbow on the same side of the sun. I will always see it on the opposite side of the sun. So if the sun's obviously on this side, then I'm going to see the rainbow over here. Now, the sun is, of course, not the only way that you can make a rainbow. Anytime you can get water droplets suspended in the air, you're going to see this effect. And you may have seen this if there's like a sprinkler or something that's putting water up into the air, like somebody's watering their grass or something like that. You will usually see a rainbow through that as long as the sun is on the opposite side from where you're looking. And with a stream from a sprinkler, that's pretty common that that's going to happen. So you're always going to see this rainbow then on the opposite side of the sun. And next time we have a rainbow, check it for yourself. See if that actually works. Okay, so as I've mentioned the word a few times, we call this property of spreading out the light, we call it dispersion. And yes, it makes pretty colors and it makes rainbows and diamonds and things like that we actually want to see, but we can also use it for science. Remember that every light that comes from the sun, for example, is white light. It's got all the colors in it. However, there are some atoms within the sun that are absorbing specific frequencies. We won't get into why that happens. If you want to, take my astronomy class. But so these specific frequencies or wavelengths are being absorbed. That means some colors don't make it out. Now, looking at the light, you can't really tell. It looks like white light because these are just very thin slits, basically, of color that's missing. And so what we can do, though, is we can spread it out using a prism. And I might get blue light down here, and maybe some green light, and maybe some yellow light. If I find my cursor, there it is. And then finally some red light, like so. So that would be white light. It's got all the colors in it. However, the sun is absorbing very specific colors. And so, let's make that black. So what we see then is there's some missing. And they look like little lines on this rainbow background. So this is called an absorption spectrum. A spectrum, of course, is the entire rainbow. but the lines that are missing here then are the lines that are being absorbed. So by matching up the lines that we see in the sun with chemicals that we see here on Earth, all we have to do is heat them up so that they start to glow, and then we're going to see that. You've probably seen that with a neon light. Then we can actually compare, and this is how we know what the composition of all the things out in space are. Obviously, we can't go out and scoop up some star stuff and study it in the lab. The only thing we get in astronomy is going to be the light, and so we have to squeeze every last little piece of information out of the light that we can, and the way we do that is through spectroscopy. So let's take a look at some samples. These are not in your book, but I want you to be able to see this. So this is the spectrum of the sun, and as you can see, it's putting out all the colors, but it's not putting out all the colors equally. The intensity, remember, is the brightness of that particular color. What color is the brightest from the sun? Well, if you look, that's going to be right about here. And that's going to be this yellow or yellow-green from the sun. This is why the sun looks yellow. It's putting out all the colors, but it's putting out more yellow than anything else. And we can see that when we run this through a prism, through a spectroscope, that spreads the light out so that we can see all of these different colors. Notice also there's a peak right here. This is actually in the infrared. And so this is outside of the visible light. You can't see it with your eyes. However, we perceive infrared radiation as heat. And this is why the sun feels warm to you, because it's putting out a great deal of infrared energy from that. Now, also notice that there are these places like right here where we have colors that are missing, and you can see it a little bit better here when you look at this. Those are those black lines that I told you about. The pattern of black lines corresponds to particular elements, and unfortunately each element doesn't have just one line. That would make it easy, but for example, let's look on the next page here. This is one particular kind of light. This particular one is hydrogen. Now, notice here that I've got a black background with colored lines. That's just because instead of taking a rainbow, taking white light and shining it through the material, which I could do, I could shine that through hydrogen, then I would see this rainbow with the black lines. Instead, what we do is we heat that gas up. And if you've ever seen a neon light, this is what you're doing. You're running a bazillion volts of electricity through it. And so what we see then are the transitions in those atoms. That's giving off the light of those specific frequencies. They're the same frequencies, same wavelengths that it would have absorbed if I were shining white light on them. So the pattern is the same. So if we look at the intensity diagram here, we can easily see that the red line right here is going to be the brightest with the hydrogen spectrum from that. So by looking at these patterns, then we can tell. Now let's take a look at another one. This is what's producing a absorption spectrum that we talked about. We've got this hot, dense, glowing object. That's going to produce the rainbow that we see. And now we put the cooler gas in front of it, and now we're seeing those absorption lines that we see. And when we look at the spectrum here, plotted on an intensity wavelength graph, now you can see that we're getting these dips like you saw in the picture of the sun. So the sun is actually composed of, we call it, simplifying a little bit, but two different elements. We've got the core, and then we've got the atmosphere. The core is where nuclear fusion is taking place. And so it's very, very hot, very, very dense. Has to be dense to squeeze those atoms together. It's about 10 million degrees. The atmosphere of the sun, which makes up most of the sun, is considerably cooler. It's maybe about 5,000 Kelvin in there. And so that's hot, yes. And yes, anything that goes through that's probably going to be vaporized, but it's a lot cooler than the 10 million degrees in the core. So this super hot, dense, glowing object then is producing white light. That white light, though, moves through the atmosphere of the sun, and it absorbs those specific colors that we saw on the previous slide with the sun spectrum. And so each element that's in the sun absorbs its particular pattern from that. So let's look at some specific patterns that we see with this prism that was produced it. And so this is hydrogen. And so this is an absorption spectrum. So we've lit it up with a background of white light, all the colors of the rainbow. It's shining through this hydrogen gas. And then the hydrogen atoms are absorbing all four of these lines that you see. And we see this actually when we look at the sun. And in fact, these are the most prominent lines when we look at the sun, and this is how we know the sun is mostly made out of hydrogen. So anytime I see this pattern, then I know that there's hydrogen present. Another example here is water. And this is what we're looking for when we're looking for alien life. From as far as we know, where there's water, there's life. And that's been true on Earth, even in places where we didn't think life could exist, like down at the bottom of the Marianas Trench, the deepest place of the Pacific Ocean. The pressure there is phenomenally high. Little food trickles down to that. And so we figure, oh, it must be barren. There must not be any life at all. And yet, when we sent our submarines down to explore, we discovered a wide variety of life. And in fact, some of that life looks more alien than something George Lucas could have come up with. So what we want to do then is we want to find water on these alien worlds. NASA's strategy for finding alien life is basically follow the water. Wherever the water is, that's probably where you're going to find the life. So we're looking at the light reflected then through the atmosphere of a planet. So let's say that this is our alien planet, and it's got an atmosphere, which obviously is going to be very close to the surface of the planet, and it has a star, and that light shines through the atmosphere, and then we see it in our telescopes here on Earth, right? Now that's still going to look like white light. However, if we spread it out using a prism, then we're going to see the rainbow and we're going to see the absorption spectra, and that tells us what elements are present in the alien atmosphere. If we see this pattern right here, then we know that there's water, and hey, this is a good candidate for finding life. So now you've seen why we get different colors of light when it passes through a prism, or a diamond, or water, or pretty much any other substance that you might have, and how that spreads that light out, because the blue light is going to be refracted at a different angle than the red light. This is pretty, as we said, but it's also got some very powerful scientific applications, not just in astronomy like we talked about, but here on Earth as well. Anytime you have an unknown substance, you can do spectroscopy on it, and then you can figure out what that substance is composed of. And this is done in a lot of crime labs. So if you've ever seen CSI and they put the sample in their little machine, that's what they're doing, is they're actually doing spectroscopy. It's an automated form. We heat the sample up usually. We can also shine the light through it and get an absorption spectrum. And then by looking at the individual lines that are produced, we can identify the element. So prisms seem like a very simple kind of device, and they are, but they have far-reaching implications, both in space and on Earth. We'll see you next time.